is going to be our last talk before the coffee break, and what I would ask is that we wait to the end, and then we have our coffee break, and we'll pick back up at 3:15 with the second half of our session. So this talk is going to be Adaptive Template System, Data-Driven Feature Selection for Learning with Persistence Diagrams, and it's presented by Luis Polanco. Thanks.
Yep, so hello, I'm Luis, and I'm going to basically, in much of the same vein of the previous talk, I'm going to talk about a way of selecting vectorization options on persistent diagrams to solve machine learning problems. Just to give a rough context of where do this work fit in the pipeline of from data to machine learning. So we start with raw data. We, as usual, did some pre-processing to obtain like clean, useful data. Using persistent homology or cohomology, we obtain persistent diagrams, from which we obtain vectorizations or collections of features, from which we want to learn, like do classification problems, regression, so on and so forth. And the main focus of the work that I'm going to present that is basically on the process on how to obtain features and how to obtain vectors. So how does this pipeline look like in real life? Let's say we have a collection of proteins. We can compute out of them persistent cohomology. Let's say we have the position in 3D of the atoms of a protein, and then we compute persistent homology. And using the features that I'm going to describe, we obtain like actually really good results. These are our results compared to the state of the art of hand-picked features that are meaningful to the field. So let's start. Let's backtrack a little bit. So let's say that we start with a persistent diagram. And let's say that I have a function, like a compactly supported function in R2, which I'm just represented by that little domain. Out of these two objects, I can define this new function that basically gives me a diagram, and it spits out a number. And if you look at what this function is doing, it's just basically, you can think of it, big quotation mark, as integrating the function f against the measure given by the persistent diagrams, meaning just the multiplicity. That's all this function is. And throughout the rest of this talk, I'm going to call these functions templates. And the reason why I'm going to call it templates is because the way that I'm going to use them to obtain features is I choose a certain domain type and I move it across the wedge or R2 to actually obtain the featurization or vectorization. So they're called templates. So I have a template, I fix a template, and then I move it around. So how do we do this? So we have a theorem that gives us basically the background that tells us why it is possible. So we begin with a compact open set with a compact set on the space of persistent diagrams. We have a continuous function in that compact set, a real value continuous function on the space of persistent diagrams. Now what this theorem tells us is that basically I can find a polynomial and a collection of template functions, basically a collection of just these functions that I'm moving around, where I have a nice pointless approximation of the function that I want. So, and if you look at this, this looks like a Stone-Weierstrass kind of theorem. It's basically telling you that for a certain collection of template functions, they're dense enough in the space that I want so that I can approximate any function as I wish. So, and then again, this new f looks weird, but again, it's just like an integration type of operator. So there are a couple of questions that this theorem doesn't give us. First, how do we find the collection of templates? And second, how do we actually find the polynomial? And the second question is easier to answer. It's basically, we're going to use machine learning. For this work, I'm going to restrict myself to basically least square problems, in a sense. But the main focus is going to be to answer the first question, how I'm going to find this collection of template functions. So, we begin with a persistent diagram. One approach that's been done before is, let's take the basically binning approach, is just dividing this space in a grid, and we can put either like little tents, like pyramids, or the vertices, or we can do two-dimensional interpolating polynomials somehow. If you have questions, I can go through how these interpolating polynomials are, and I can move them around, again, so that I obtain the desired collection of functions. I'm going to call this type of approach of like, I have to make choices of how coarse or my grid is and that kind of thing, and an adaptive approach. And the actual approach that we want to take is what I'm going to call an adaptive approach. And let's imagine that I have a collection of persistent diagrams with labels, in this case, for example, and in this example, the colors correspond to the labels. What I like to have at the end is a collection of regions that come from my original collection that kind of highlight the important regions for my specific machine learning problem. In this case, what I'm going to obtain are like these Gaussian regions, just ellipses, and I'm going to put like Gaussians on top of them as my template functions. So, now the question is, how do we obtain my regions? We took different approaches. So the first approach is kind of, let's try Gaussian mixture models, which is kind of a standard procedure to try to fit Gaussian domains to a dataset. What if we try HDO scan, which is kind of a density, non-dependent, and like robust to outliers approach to find the regions? And what do we use CEDAR? And CEDAR is basically a current tree algorithm that is trying to minimize a notion of entropy for the current tree that you obtain. So it's basically looking for a current tree with a minimum notion of entropy in it. And one of the main results that we obtain out of taking all these approaches is that CEDAR provides a more robust set of features. And something that I didn't mention here is that if you're familiar with HDO scan or the scan methods and Gaussian mixture models, they're super expensive to compute if you have thousands and thousands and thousands of points that you expect to have like in a collection of persistent diagrams. And CEDAR is really time efficient for the purpose of the examples that we present. Yeah, so let's look at this the examples. So the first one that we have is a manifold classification problem, and this is kind of a synthetic example. What we're doing is that we're taking six different manifolds, an annulus, a cube, three little clusters, three clusters, two clusters, a sphere, and a torus. We generate samples of 200 points around or these manifolds, and then we generate multiple samples of those. We compute persistent diagrams of those, and then we want to do basically we want to solve the classification problem of finding out which point cloud corresponds to which manifold. And in all of these results, I'm going to always select 70% of my data for training, 30% for testing, just so the results seem fair. And these are the results that we obtained. And HDO scan, GMM, CEDAR, again, my adaptive template results. And they're in contrast to results obtained by Perea and Kawaner in a previous paper that is it's one of the main motivations for this work. It's hard to read this table, but what is important for me to point out is that even though this looks shape classification, and this comes from the Shrek 14 mesh shape dataset, which is basically a bunch of meshes that correspond to people in different positions. And the classification goal is basically you have 5 different positions for 3 different models, and you want to solve the 15 classification problem. How do you obtain persistent diagrams out of this? So you do a hit kernel signature on these meshes, and then you compute the sublevel persistent homology of those functions. And these are the type of results that we obtain. And let me explain a little bit what this table means, because it looks confusing. So whenever you're doing hit kernel signature, you have to select a way to subdivide the time variable, which is basically just a parameter that you have to select. What this is the way that we did it, or that the data was given to us, Like they made 10 selections for different values of the time separation, time discretization, sorry. And we run our classification problem for all those 10 different problems. So, and what, for example, this first being Staliness is then in 6 out of those 10 different classification problems, CDR beats GMM and HDV scan in classification and accuracy. And what I'm presenting here again is just a combination of different methods. All of these are like kernel methods. So I have different methods, different kernels, and random forest rows because it's a standard.
5 minutes.
Yeah. And what we see here is basically that CDR is a very robust, again, method to obtain feature vectors across different combinations of kernels and models. One thing that I should mention is that, then again, as probably said before, on the background, and we're also doing different select, like we're basically doing a grid search for the parameters that you need to use on the kernel and on the model, and all of these are regularized models. So I'm presenting the best possible results obtained. And finally, let's look at a more real kind of example. So this example is a protein classification task. So we take a data set from the protein classification benchmark collection, which has just a collection of proteins, and it has 55 different classification tasks. And again, we want to solve all the classification tasks, and we want to compare to the state-of-the-art results. And as I mentioned before, this is related to the first example that I gave. I have a collection of proteins. I have the R3 position of the atoms, and I use that to build basically wave separation and compute persistent homology. And then I use the different methods that I mentioned to actually compute. And this again is the same table that I showed before, but what should be noticed is that we have quite a difference on classification accuracy once we use this adaptive approach to find the feature map of the collection of features. Sorry. So, what did we get out of this work? So, the main goal was again to find or to approach the feature selection characterization problem in a way that I don't have to, that it's informed by the data I already have in terms of the persistent homology or the persistent diagram that I obtain. We use different approaches to find these actual possible features. And we, again, as I mentioned before, find out that CDR is not only the most robust, but it's also the fastest to compute if you have a lot of data, as you expect from this type of problem. And this is the exact robustness result that I mentioned before. Oh, there is one thing that I would like to mention here that I forgot to put, and is that either for GMM and HDV scan and a lot of these like region selecting methods, again, they have parameters that you have to choose to actually tune the algorithm. So for GMM, you kind of expect to know more or less how many Gaussians you can fit. For HDV scan, which is just a hierarchical method, at some point you have to do some pruning. So again, you have this parameter to choose. CDR doesn't have that. It's running on behind and it's like behind the hood. It's trying to solve an optimization problem by minimizing entropy, and that's basically the way that the algorithm on itself chooses the optimal coverage. So for CDR, we don't have, like, we get rid of one of the parameter selections at least. And what we just show is that across different combinations of kernel methods, CDR seems to be the best option. And as I mentioned it before, HDV scan and GMM can be really expensive to compute for this type of data set, where basically you expect to obtain, like for a single point cloud, you expect to obtain a persistent diagram with possibly many, many points on it, and then you have collections of those on top of each other. So this region selection can be a really computationally intensive process. So the reference. Awesome.
have time for a couple questions before we go to break.
Did you find in your application that you were pushing the limits of the scalability of Sphere? I know you mentioned that it outperformed these other methods, but
yeah, it's like, at least for the protein, like the manifold classification, definitely not. This is super. It's kind of a proof of concept example. For the Shrek 14 dataset, the shape dataset, it definitely doesn't, but none of these methods does really. It's kind of easy to compute, and definitely a protein example does push here to one of its limits. It's starting to get slow, and that's, I mean, I didn't mention it, but for this example, I never presented results with GMM and EGScan, and it's just because I just exhausted the computational power that I had available at the time.
So one more question back here, and then we'll go to Ryan.
So I hope I haven't misunderstood the fundamental idea, but if you could go early on to the theorem that you're basing your idea on, is it true that the statement is there exists? Okay, yeah, there exists a capital N,
yep.
Right? So do you have A, some theoretical idea, or B, some kind of heuristic intuition about how big N has to be in practice? Like how complex? What's the complexity class, so to speak, of for a fixed N? How much can you get?
Not a priori at all, because you don't know. Basically, since we are doing, like, the N is going to basically come from the collection of. Basically, a collection of persistent diagrams that you're going to have. So, if, for example, for some reason you obtain that the collection is kind of covered like a huge connected piece, like you will expect to need a lot of N's because you want to select like little regions that actually contain the features that you expect to solve the classification problem. In this case, you wouldn't expect that many. You will expect, like, probably or most likely to highlight like the intersections or the place where the intersection is the less abundant, so that you can use those basically as your features to classify. So the answer is there's really nothing there.
We have one more question.
Yeah, so I mean, there's a follow-up to the other question is you mentioned that there is some sort of computational limitation that you're approaching. What's driving that? So what is the bottleneck there?
Okay, so the bottleneck, at least I'm aware of the EGScan bottleneck. What EGScan is doing is I don't know if you're familiar with the EGScan methods, but EGScan is basically building a tree of different DB-scan solutions. So it's basically trying to find clusters, and the way that DB-scan find clusters is by defining a specific metric between the point clouds. And it depends on a parameter that you're changing. What EGScan is doing is changing that parameter and building a tree on top of that. So it has a lot of, it's trying to build trees and it's trying to do that on top of other things. So that's why that one is computationally extensive. GMM is trying to solve an EM problem. So it's like a expectation minimization problem that's always done in 2 steps. That makes it super slow. All of the minimization steps, like a gradient descent thing, and it gets slow. And I don't know if that kind of answers.
Well,
yeah,
we can talk about that a little bit afterwards.
All right.
So let's thank the skip speaker one more time.